Okay, let's get started. And welcome to the IMS Medallion Lecture I. I'm Jiju. I'm a professor in the Department of Statistics at the University of Michigan. I'm also the IMS representative on the JSM program committee and also the chair for this session. So let me start with introducing our Medallion lecturer, Annie Chu. I'll read a short bio about Annie. So Annie Chu is a Chancellor's Professor in the Department of Statistics at the University of California, Irvine. She received her PhD in statistics from the Pennsylvania State University in 1998. Chu's research focuses on solving fundamental issues regarding structured and unstructured large-scale data and developing cutting-edge statistical methods and theory in machine learning and algorithms for personalized medicine, text mining, recommender systems, medical imaging data, and network data analysis for complex heterogeneous data. The newly developed methods can extract essential and relevant information from large volumes of intensively collected data, such as mobile health data. Her research impacts many fields, including biomedical studies, genomic research, public health research, social and political sciences. Before joining University of California, Irvine, Dr. Chu was a data science founder professor of statistics and the director of the Illinois Statistics Office at the University of Illinois, Urbana-Champaign. She was awarded the Brad and Karen Smith Professor Scholar by the College of LAS at UIUC and was the recipient of the NSF Career Award from 2004 to 2009. She is a fellow of the Institute of Mathematical Statistics, IMS, the American Statistical Association, and the American Association for the Advancement of Science. She currently serves as the co-editor for Journal of the American Statistical Association, JASA, Theory and Methods, and also as the IMS Program Secretary from 2021 to 2027. So today, each year, IMS nominates 8 Medallion lecturers in fields across the IMS subject range. The award of a medallion signals the honor inherent in being selected to give one of these lectures. So IMS awards the medallion to Annie Chu and invites her to present a medallion lecture entitled Data Integration for Heterogeneous Data. And there's actually a real medal, so now let me present this medal to Annie. Yeah, so now let's welcome Annie to give the talk, Medallion Lecture, Data Integration for Heterogeneous Data.
Okay, thank you, and Ji, for a very kind introduction. Ji's also very my good friend. And it is a great honor to give a first medallion lecture for this GSM. And I'm very grateful to IMS Selection Committee, the name Lecture Selection Committee. And some of you might know that I spent 9 years at Oregon State. So today, it is really feeling great to come back to Oregon, Portland, to deliver the medallion lecture. And I see a lot of my friends and students and colleagues are here. And thank you for your coming and your support. So before I go and talk about data integration, I want to talk about why I'm interested in doing this type of research. So about a year ago, I worked with a Penn doctor. Actually, he's very famous. He reviews the autopsy report for Michael Jackson. So he told me that there are a lot of people suffering pain which is non-treatable, not disease-specific pain. The 4 major pain for the adults is headache, abdomen pain, back pain, and joint pain. You might suffer one of these 4 pains, And me too, sometimes. We're getting older. And see, a lot of these pains is not really treatable, chronic. And he's saying that you have pain, I have pain, he also has back pain, I have some back pain. Maybe we can learn from each other, from each other's pain, and find something useful. So he suddenly opened my horizon. I realized, as a statistician, can we handle the data that really very diverse source? That a doctor might be studying one kind of pain on their study, and the other doctor collecting other type of data. They could have very different, unique covariate information and unique response information. But can we still do data integration? I raise this question to you, okay? So, and then we look at the literature about the data integration, and we saw this is a very vibrant and a growing field for statistical publication. If you look at the keywords, data integration, compared to 2 decades ago, about 2000, it's tremendous. It's about 4 times more. And the typical statistical publication, including a lot of trendy ones like genomics, machine learning, deep learning, they're about less than 3 times compared to 2000, right? And this phenomenon even more popular in applied field. For example, the marketing. I know some of you in business school, econ school, in the marketing field, the data integration, these keywords actually is 12 times more compared to 20 years ago. You might ask why, right? And because, very naturally, because we can access more data. We have the luxury to access more data. So it's kind of a dilemma. You see, we have more data, so why do we need to do data integration? We have more sample size. Why do we need to borrow information from other sources? I will come to answer this question a little bit later, okay? So actually, this data integration is not a new concept. Even back to 1904, Pierre Carlson already published a journal paper called British Medical Journal, talk about meta-analysis. Actually, if you look at citation for meta-analysis, it's tremendous. It's like maybe statistics, one of the most popular citation is meta-analysis. So you look at this very old paper, 1904, more than 120 years ago. In this paper, specifically, Carl Pearson mentioned about the 2 specific subgroups. One is the Indian experience. One is a South African experience, okay? They study certain fever, and they mentioned this one particular subgroups in South Africa is very, very small, okay? Mention the words small. And therefore, it's very difficult to draw the definite conclusion. And also in this publication, they mention about the heterogeneous, okay? So heterogeneous is not like it's a fancy, trendy word. It's already appeared in 1904. So why we, in that time, seems very natural. Why do we need to do data integration? Because often we have very small sample size. And based on small sample size, you might don't have very conclusive conclusion, the result, or your p-value is not significant, right? Doctor wants to see significant treatment result. They say, I need to pull more information. So one thing I want to talk about is data integration. The foundation, of course, you have some common information you can share. But the challenges here is a heterogeneity. So this I come back, why we have so many data, right, these days. We have all kinds of data. We have a multi-source, multi-modality data, structured, unstructured data, text data, video data, audio data. However, we have a lot of heterogeneity. The data itself is very noisy, and the signal could be very, very weak. The signal weak is actually masked by this noise. And often we heard about people say garbage in, garbage out, right? Why we talk about this is to talk about the data quality is poor. Now, on the other hand, I think we shouldn't have this kind of perspective. I think if we always think about the data as a poor quality, I cannot do anything about it. It's a wrong thinking. It's a really, we should ask ourselves, can we find the right tool to discover the inner value of the even noisy data, okay? So this is, I'm going to talk about the data integration. So we view this data integration as a game of a seesaw, okay? You have kids, you play seesaw when you were young. So one's a homogeneity, one's a heterogeneity, right? In many examples, homogeneity outweighs heterogeneity. I will give you some example. Why is the homogeneity outweigh heterogeneity? And I believe a lot of us actually analyze data with this kind of situation, that we have a similar mechanism or similar correlation-dependent structure. So therefore, we can borrow information from this, the homogeneity data. But on the other hand, we also have a heterogeneity. I'm going to come back, talk about the heterogeneity more later, okay? This is showing some example that we have homogeneity and also have a heterogeneity, but homogeneity actually outweighs the heterogeneity. Let's look at this Alzheimer's disease neuroimaging initiative. I know a lot of you actually analyze this data called ADNI data. This data is very interesting, and our group, my students, also analyze this data. It certainly has a homogeneity because we know the Alzheimer's patient share common this neurological mechanism, the progression, right, getting worse and worse. We know something in common. There are a lot of discovery about Alzheimer's patients. But in this data, we also have heterogeneity in a sense that the different subjects, they're collecting different number of the modality. So you can see this, we call the block missing data. That some subjects maybe had all the information, had the luxury, have all the information, but often some subjects only have one type of a data. Let's say have the PET data, but doesn't have MRI data or don't have a genetic information. It's very common, right? Either doctor say you don't need it, or the hospital facility don't have the capacity to measure this genetic information from you, right? So you can see we have this heterogeneity going on due to the multimodality. Another example, I'm going to talk about the mobile health data, because in recent several years, my team and I are working on this mobile health data. So I want to show you that this is the Oura Ring data. Maybe some of you wearing the smart ring. It's not a wedding ring, has a lot of sensor, okay? So even such small ring is able to collect very rich information. For example, your physiological information. So for this kind of a data, we have also homogeneity. In what sense? In a sense that the correlation structure or correlation information among all these multiple time series data are very, very similar, even from different subjects. Why would I believe that, okay? So suppose you have a fever, okay? So I actually did have a fever in the May when I go into conference. And I noticed that my heart rate also goes high that night. And my sleep quality, terrible. And my respiratory rate is also very high. Turns out what? I got a COVID, okay? And actually I have almost minimal COVID symptom. But the mobile health device picked it up that night, every of my data just abnormal. Okay, so this I'm telling that if your temperature is high, your heart rate and everything is also correlated, okay? So this is the homogeneity part. The heterogeneity part is that we have multi-resolutional data. So even you use a wearable device to measure all this kind of many time series data, they are not measured in the same interval, okay? Just think about your deep sleep, REM sleep, light sleep only measure once a day, but your heart rate, your physical activity measure much more frequently, okay? So you have a different resolution. And also for different subjects, we could, remember it's an observational study. I cannot force someone, let's say, gee, you have to wear the wearable device all the time, right? So sometimes people not wearing the wearable device, and therefore the different individual, the trajectory could also be very different. Could be due to the different stress kind of cope with reality. Some is a morning person, some is an evening person, right? So all this heterogeneity you can imagine even within the time series and across subjects. I give you more example about this, actually, this neuronal activity data for our team. So we have a neuroscience team in UC Irvine. They study the rodents, rats, okay? And actually, we only have 5 rodents, okay? You wonder why such small sample size. Realize it's a very expensive experiment. Even for 5 rodents, it could cost NIH $1 million, okay? Multi-million dollars. So what they're doing is that for each rat, they implant this electrical tetrodes on their brain, try to measure their neuronal activity over the time when they do smelling. And it's a very challenging task. They do very quick sequence of the different odors, the smell. And then the rats have to recognize it's an in sequence or out of sequence order, right? Just I ask you to smell 5 different smells, and if you can memorize, next time I still use this 5 different smells, but with the wrong sequence, can you tell, right? It's very challenging for humans, but rats actually can do pretty well. And in the meantime, they're recording this neuronal activity, okay? So here, there's some homogeneity. This is a graph drawn by our team that latent representation for the different odor are quite unique, that actually they resemble for different rats. They have the neuron spiking. But on the other hand, there's a sequential path could be heterogeneous across different rodents. You wonder why? Because remember, even they are rats, they were selected as a homogeneous rat. They are male, same age, right? But still, their learning ability is different. So therefore, this sequential learning path could be different. So here, we're showing this geometric diversity. Actually, we're going to come back to this example. How can we do data integration? Okay. Now, the second part, I want to show the examples that the data actually show more heterogeneity compared to homogeneity, okay? So in a sense that heterogeneity, because we're measuring different study of subjects, population, and distribution. I mentioned that the Penn study, right? We have a different study, and their covariate information are different. Their response could be very different. And so therefore, it's very difficult to impose assumption they have a complete shear structure. They might just have a partial shear structure. So give you the pan cancer analysis. So some of you might be familiar with this data. People study 5 different cancers. One is a skin cancer, and the colorectal cancer, and the lung cancer, and also pancreatic cancer, and the breast cancer, okay? So they, of course, they're collecting very different covariate information, and their response could be different. So the heterogeneity is obvious. Let's say this mutation for specific genes could be very different. We all know that for breast cancer, if this BRCA1 or BRCA2, these genes are abnormally mutated, then this person could risk this breast cancer. The most well-known example is from the celebrity Angelina Jolie. You know this example, right? And homogeneity, we know because they all study the cancer, and they find out that TP53 is a tumor suppressor. Okay, so this is frequently mutated in many cancer, or in all these 5 cancers. So they have some similarity. Now we look at this more concrete. Okay, I talk a lot of examples. The reason I talk about these examples is hopefully the study you are doing, you think there's some connection. But let's examine this with more details. So what do we talk about the heterogeneity here? So if you look at this common biomarkers, even the common, you can do in the data using neural network or using PCA to find the common biomarkers across all these different studies. So first, the marginal distribution could be very heterogeneous. And this is what we call covariate shift. And on the other hand, the conditional distribution of the response given these biomarkers across the different cancer types are also very, very distinct, and we call this posterior drift, okay? We didn't name it. If you find covariate shift, a posterior drift, you can find many literature. And another example is image classification. Now, I know if your students are doing deep learning, this minister data probably is the first data set they will try, okay? This 1989 data set in the paper by LeCun, okay, the young LeCun, and make it very famous. And so by using convolution neural network, we can actually use, now we call artificial learning, artificial intelligence, to recognize 0 to 9 Arabic number, okay? So my student tell me, say, hey, let's do something about it. Can we do data integration for the minister data and the Korean minister data? So the middle image is the Korean. I know some of you are Korean. I don't recognize this. Maybe I only recognize one. Looks like 8 to me, but I'm not sure it's 8, okay? And also fashion minister. The reason they call minister because they're all doing the labeling, right? So here we have the heterogeneity from both covariate shift and the posterior drift because their marginal distribution are different. And the labeling could also be very different. Fashion minister is labeling a lot more information than just a 0 to 9, okay? So, but they also have some sharing homogeneity across these three subjects. We recognize the edges, curves, and strokes. It could be shared, this information. If you do some neural network and finding out the latent representation, this information can also be borrowed. And we're going to come revisit this example in our data analysis. So I'm kind of summarized so far. I talk about heterogeneity in modern data integration. So the heterogeneity source come from two, observational. Observation in a sense that data was observed, really self-selected, right? We have no control by experiment design. So therefore, we see the data have a block missing. We see the data like a multi-resolution, this type of a data, because we're dealing with observational studies. And the other part is about distribution heterogeneity. And the previous examples, we're saying that distribution across different data sources are heterogeneous, right? Including covariate shift, geometric diversity, and the posterior drift, this type of example. So I'm actually coming to existing literature because in data integration, we mentioned a lot of existing literature. So she made a very good figure, say we are standing on the shoulder of the giants, okay? This figure is generated by ChatGPT, not surprisingly. So first, we're going to, all the literature, I'm actually cannot exhaust all the literature, but as the most popular, I think it's a well-known literature. First one is a meta-analysis. Meta-analysis, the idea is very, very simple. So assume the true effect size is either same or similar across the different data source. Can we increase the statistic power or generalizability? In a sense, the standard error can reduce the standard error of the effect size, right? So even though maybe particular one study show no significance, but if I pull all the information together, I show the significance of the treatment. But often for meta-analysis, the heterogeneity introduced by study design population are ignored, right? And also, the different studies, they adjust the confounders in different way. And not even mention the unadjusted, unmeasured confounder. There's no way you can adjust unmeasured confounder here, okay? And want to point out the literature Hedges by Okin. I actually just checked yesterday. This citation, the book is over 20,000. So it's a lot of citation, a lot of visibility. Another one is about matrix factorization. So this is also very well known, the joint and individual variation explained model by Eric Locke, okay? You might have heard about the Locke, for Locke, wrote a book about unlock the data of a power, if I remember correctly. So it's very easy to remember. So this is a very cool technique. They're showing this, that the data matrix can be factorized into two parts. The first one is a joint structure, which can be shared across the data. And the other one is individual structure. okay? And so in their approach, they really more focus on this covariate shift, okay? They're not really focused on posterior drift. And also they believe these sharing patterns are pre-specified, okay? So this is interesting literature if you work on data integration. Another one is about multitask learning. This work is done by my good friend, Peter Song, and his student, Lu Tang, in 2016. I think it's a Journal of Machine Learning Research. So for this paper, they really focus on posterior drift, that the coefficient for different data set could be different. So that means the association between the response and X is that cross subjects, cross the data are different. Okay, so that's why you show the beta 1 estimator is different across a different data source. So the idea is using fused lasso learning to do the data fusion to pull the similar coefficient together. Okay, so advantage of the approach that they're able to explicit and smooth control the balance between the homogeneity and the heterogeneity. Then also, I think recent very popular work is called transfer learning. Actually, JADA didn't receive a lot of paper by transfer learning. I feel it's like maybe trend is shifting from causal to transfer learning. It's very interesting, okay? So this transfer learning, the whole idea is about aggregate informative auxiliary source data. It's through this called the bias correction to improve this estimation efficiency on this target data. So the focus is on the target data, and they try to learn something from the source data. Okay, so you can think about this type of literature is more focused on posterior drift. And also, I think Regina is probably in the audience and sitting there, and I'm also talk about the fusion learning, which she is also going to give a fusion learning lecture tomorrow for the Elizabeth Scott lecture. Okay, you can find out more details through her talk. I think it's very, very challenging to do fusion learning for inference. Okay, here we actually, today my focus is not about the inference, it's mainly about the prediction and estimation part, because for inference, you need to require more assumptions. You need to have at least a distribution to figure out the inference, okay? So in their work, the idea is they try to construct a joint confidence distribution to integrate multiple heterogeneous distribution for efficient inference. In a sense, they can reduce the variance, okay, by pulling all the similar distribution and also remove the irrelevant distribution. I think this is the whole idea, to avoid the bias. So in their approach, they can handle both covariate shifts and the posterior drift. Now, also, I know some of you work on the optimal transport, including me. So we talk about this data example about the neuronal encoding for this sequential neuronal activity when the rats do the smelling, okay? So we see that they have a geometric diversity. So optimal transport is able to project this diverse heterogeneous neuronal encoding to the common latent space. So therefore, you can align this information together. Otherwise, every subject is in different latent space. So all OT is try to align them well, okay? So it's really try to deal with geometric diversity. And also, we mentioned this adenine data. So this multiple block imputation approach, the idea is that you try to impute the missing block using other data source. Okay, so for the paper developed by Fei Xue and I, and published in 2021, we find something I thought it's very, very interesting, that we not only utilize the data, which is with a complete observation, we also can integrate the data, let's say the green data, with a missing in the middle. We can also integrate that information to help to impute the missing data for the yellow block. and also the blue one, but not the pink one, okay? So if you want to learn more details, you can read that paper. But this, I'm telling you that we can do multiple block-wise imputation to integrate a different source of data. And this is for mobile health data, that we have a different resolution for different time series. How can we borrow information together, right? So the idea is that we're using this dynamic latent factor model to project the raw observation to the latent space. So therefore, this correlation information among all these latent observations variables can be incorporated, okay? So this is for the multi-resolutional data. So I'm kind of summarized. Of course, it's not including every literature, but I think it's literature is a relevant one here. So the summary of the existing method really dealing with the heterogeneity through two approaches, main two approaches. One is to try to alleviate heterogeneity. Alleviate is in sense that we try to extract the sheer common information, try to ignore their heterogeneous information, turn down the heterogeneity, so discover the common structure, utilize it to make it a better pattern discovery or interpretation. This is one approach. This including meta-analysis, OT, and matrix factorization. And the other stream is more like, I'm going to harness heterogeneity. This is something I really like. So when we talk about data integration, we not just want to discover common things. We also try to explain the heterogeneity, why this person is unique, right? We want to learn the uniqueness. And here is to try to borrow information across heterogeneous sources to improve the predictive or inferential performance. You might think it's impossible. I'm going to come down this, why it's actually doable. Okay, so this also including the literature like multitask learning, imputation, fusion, and also optimal transport. So this is a summary of existing methods. We can sort of like three major categories: a block missing, matrix, covariate shift, and a posterior drift. And many of the approaches just can address one or two. Very few of them can address all of them, okay? So if we can address all of them, we can utilize much broad range of data sources, right? We can do more, not just like this specific data structure. And the last one, actually, I was very interested in trying to answer is, can we learn heterogeneity from diverse sources, okay? So here's a goal. I try to summarize what we try to accomplish. We try to build a unified framework to accommodate multiple types of heterogeneity, including covariate shifts, posterior drifts, and block missing. This actually including many types of data. Just think about your covariate information could be quite different, response could be very different, and distribution of covariates is different, and dependence information are heterogeneous. Okay? And we try to improve the predictive performance and provide interpretation for this sharing structure. And this is kind of details, and this is actually not my focus, but you can do more under this kind of framework. So let's look at the problem set up. We have a covariate X, and we call this XS because it's a source specific, okay? The different subgroup, different data source, or this is stomach pain, this is the headache pain, this kind of different data set. And the response, YS, is also source specific. It's a different response. And so we try to see cross different data source. We allow the distribution of a same covariate can be distinct. We call this covariate drift. And across a different data source, this conditional distribution of the response is also different. We call posterior drift, and also missing pattern could be all different. We call the block missing. So first, we can talk about how can we address this covariate drift and the posterior covariance shift and posterior drift. We call this representation retrieval, R squared, the different R squared, like typically you learn in your statistic book, okay? We call R squared learning. So first, let's see how can we understand the heterogeneity from matrix factorization, okay? So if you do the matrix factorization for dimension reduction purpose, for extract informative information, you can use a PCA, can use autoencoder, deep learning, this type of a tool, okay? So typically in this kind of matrix factorization approach, when they try to address heterogeneity, they often assume either column vector or the row vector are common, can be shared, and the other one is heterogeneous. And we rarely see the literature that assume both U and the V are both heterogeneous, okay? But reality, if you look at this example, okay, look at this 3 minutes data, image data. We can use ResNet, extract this latent information, let's say about 512 dimension of a matrix data. And we look at the pairwise comparison, kind of finding the concordance for this row vector or column vector. And what you see here is, let's say, the first minister data and the Korean minister data, you see some concordance, right, directional concordance. That means these 2 data sets, they share something in common. If you see this diagonal information, you have a lot of dark color, means a very high similarity. But if you believe one of the column vector or the row vector, they should be common, you should see that the whole diagonal matrix, right, should be the all identity. But reality, no. So now if you look at the minutes data and the fashion minutes data, you actually didn't even see very strong correlation at all for this row vector or column vector concordance, and similar to Korean minister and fashion minister, right? So here what we see, no singular vector are exactly shared among all data sets. All data set means 3 data sets. However, some singular vectors are similar among 2 data sets. And if you look at the pan-cancer data correlation, we have 5 pan-cancer, and we also do this pairwise, right? We find a similar pattern that only first the singular vector is shared among all these 5 cancer. Not surprising, we talk about this one gene, the TP53, right? So it's kind of shared by all these 5 different cancer. But we also notice that some singular vectors are similar among this, a subset of the cancer type, okay? So here we actually talk about this motivated paradigm. So everyone knows about the blind man touched the elephant. I don't need to repeat that story, right? But actually I see it differently. I mean, this is talk about blind man touch the elephant. I mean, think about the old days. How many people really have seen the elephant with their eyes, without a newspaper, without zoo, right? Because elephants are very limited. The sample size of the elephants is just very, very small. So it's not surprisingly if people, when they, even the blind person, if the person with the eyes, they can see, they will try to find some similarity from their real life experience. And real life experience in their common life, the snake is very common, they can see, the fan, the tree, the rope, the wall, and the spear, right? So by saying this, that I try to say that if you want to find the data set, they have to share every information. We end up with very limited data size, like the samples of elephants. But if we're able to keep our horizon open, we say at least some partially structure or partially information can be shared, then we can really, including many more data sets, not just elephants, we can have other kind of image data, okay? So here, we're talking about fully shared structure and the partially shared structure. And our approach really focuses on using partially shared structure, we can achieve more, okay? So here is a method preview. So on the left side is your true data representation. This true data representation often is unseen. And this is what I always tell my students. These are your inner beauty that maybe is not observable. And for the data, is the inner value for this data. It's unobservable, right? You sometimes criticize the data quality is poor because you didn't see the inner value for this data set. So our idea is try to pull all this information in this representation dictionary. I'm going to get all the information from these different data sets and get their inner value for these different data sets. And you can see that, let me move on to the next one. This dictionary, some of the color, right, it can be shared among all this data set. For example, the light green color, this feature are shared by all data set. But some color just shared by 2 data sets, for example, the blue one. And some feature, let's say dark green color, only is from 1 data set, V3. Okay, so we use this dictionary to get all this information. So then we try to get retrieval. That's what we also try to learn the heterogeneity from this specific data, right? Eventually we need to draw the conclusion for this specific pen. It's a common pen, maybe we learn, but still we need to answer the question for this specific data. So the learnable for V1, we can retrieve this inner value information from this representation dictionary, okay? So you have to retrieve. So this is kind of a conceptual idea what we try to approach. So here I actually try to show that how can we learn heterogeneity? Often you might see this kid doesn't look like parents. I'm not saying that the kid is adopted, okay? Often you see this kid doesn't look like the parents. Of course, this is a bad thing. I realize it's not a good way to say this to the parents, right? But we actually try to understand why this thing happened. It's because the heterogeneity play a role, that the unique combination of both parents' genetic traits and make this kid very unique look, okay? So even though by observation it doesn't look like, but actually if you really study the genetic information, could be a unique combination. So here, the principle is we try to, the representer here can be fully shared, partially shared, or uniquely shared. And you can use many different ways to learn these representers. For example, PCA, and also autoencoder, decoder, okay? So here's a representation retriever. So for first one, it looks very simple, right? We have a binary matrix. If this representer can be retrieved, then we have the 1. Otherwise, it's a 0, okay? So each data source retrieve a different number of representers, and retrievers also offer interpretable pattern discovery because we know which feature we are able to retrieve. So the retriever, this is a binary value, and so if it's just there's a 1 in the 1 row, that means if you have more than 1 in a row, that means you have a multiple data source have the same representer. If just 1, that means only 1 data source have this representer. If you have a 0, that means there's no representer for this data set. So we have this kind of notation, okay? So in order to enhance the integrative representation learning, we propose this penalization, and we call this selective integration penalty, SIP, S-I-P, okay? And she is greatly draw the picture of a sipping, okay? And also it's good, it's like a sipping your energy, whatever information from different data source. The idea is try to minimize the number of individual and no representer. So we try to encourage the integration if the representer comes from multiple data sources, but we kind of discourage if it's just no representer or just one representer, okay? So this selective integration penalty, so we can written this way. First, there's no penalty if you have more than greater equal than 2. You only penalize if it's a 0, if the share information is a 0, nothing to share, or just the 1 itself, okay? And this whole minimization computational complexity is a linear complexity. However, we have some practical issues when you do the optimization. Actually, she did try this using integer programming. Everyone tried integer programming. It's very, very slow, right? So optimization issue that if you're dealing with a non-continuous function, you have this kind of indicate function, which is a binary. It's not easy to do optimization. And the modeling issue, and we also don't believe that every feature should be completely shared. One means completely shared. You could have partially shared. That means that information just like shared weights could be between 0 and 1. So therefore, we can solve this problem simultaneously. Optimization-wise, we try to propose a surrogate SIP. And the modeling issue, we allow this relaxed representation weights can be between 0 and 1. So this is a penalty function. If you look at the Q, is a blue line, and this is, you see the surrogate approximation for the 0-1 loss, right? If the tau value is very, very big, it is very close to the 0-1 loss. And this penalty function is like when it's more than 2, you don't impose any penalty function. And when it is between 0 and 1, you put a penalty function. And in between 1 and 2, it's a smooth, it's a really continuous function. So this is our penalty function. And this R-squared learning loss function, we can write a very generic way. This, you have the response comes from this source-specific S. And you also have this learner, the FS, okay? And this is the function of your representation learning, the theta you learn from, okay? And the penalty function, what we just talked about. The loss function can be very general, let's say square loss or absolute residual loss or any kind of loss you can put in your model. We don't need to specify here, okay? So the choice of a learner, this is important. So given the representation retrieval framework, we can retrieve the representation for each data source could be different. This is something we can learn heterogeneity, okay? Because we're able to retrieve a representation from the data source or uniquely, okay? So even in a sense that different dimension of a latent space, okay? Usually you do matrix factorization, you assume they have the same dimension. Here we don't need to have the same dimension. And also we can accommodate this posterior drift, that the conditional distribution of the response given the retriever could be naturally different across data source, okay? So this is what we call source-specific learner, FS. And using the source-specific learner, FS, we are able to learn the unique conditional distribution. Actually, this is very interesting. This morning, I think Aditya talked about data fission, okay? And I'm doing data more like integration. Think about, it looks like doing very opposite thing. Once data splitting, I want to try, but actually in some principle, it's very common, okay? We can discuss later. So here, we can use a linear model, neural network, and other machine learning model can be used as a learner. So it's very generic. I'm not specifying what the FS should be. You can use whatever you feel comfortable, okay? Now, the recap about the R-squared learner, okay? So this is a great picture she generated. So we really try to encourage the representation, and so in the Lego, okay, your kids play the Lego, this is the little bricks, right? It can be reused by more than one model. More than one model means more than one data source. So you kind of, the retriever gave us, let's say if you want to build a red car, I know this kind of a Lego block. If I want to build the animal kingdom, I need a more colorful one. And if I want to build the Eiffel Tower, okay, currently in Paris, right, the Olympic game, then I need to have this specific retriever, okay? So you kind of very flexible to learn this representation and reuse them, okay, to build your learner. So the second part, I'm also going to use this idea, how to address multimodality block missing. I mentioned that early on, 2021, and Fei Xue, we already published a work called multi-block missing data. And by the way, we actually have this R coding, R package in CRAN, and recently we look at a lot of downloads. So that means that this work is very, very useful if people download the R package. So, but I think I actually can do better for using this R-square retriever. So let's look at this example. We have 3 different data sources. And the first one, we observe modality 1 and 2. And second one, observe modality 2 and 3. And the third one, observe the data modality 1. Okay? So how can we integrate all modality information across different data source, okay? Not just here, we don't have the luxury of the one data, have all the modality, which is typically required for a lot of data imputation. You need to have the complete observation from one data source, okay? So let's look at how we do it. So here we have this theta is for the representer dictionary. And theta 1 accommodates for modality 1, and theta 2, theta 3 for modality 2 and 3. And theta 4, you can think about accommodate both modality 1 and 2. You can also think about this is interaction between the modality 1 and 2. And theta 5 is interaction between modality 1 and 3. Interaction in some sense, there's some common dependence information. And theta 6 is interaction for 2 and 3, and theta 7 is a 3-way interaction, okay? We can think about this way. Now, when you look at this theta 1 all the way to theta 7, what kind of a data you can retrieve this information? So theta 1, clearly in both theta 1 and 3, we can use the data 1 and 3. And also theta 2, both in data 2 and also data 1, okay? However, theta 3 doesn't have that luxury, only appear in the data 1. And similar, you can see that theta 4 only appear in data 1 because only data 1 has both information of a modality 1 and 2. And so therefore, the theta 5 and the theta 7, it's not identifiable because we don't have the data observed both modality 1 and 3. We don't have it. And we also don't have the data observe all 3 modality. Okay, so keep this in mind. Some of the representers are not identifiable, cannot be learned. So here, what can we learn from theta 1, theta 2, theta 3, and 4, and 6? So theta 1 and 2 can be learned from multiple data sources. So theta 1 can be learned from data 1 and data 2, and theta 2 can be learned from data 1 and data 3, okay? And theta 3 can be only learned from data 2, and theta 4 can only learn by data 1, and theta 6 can only learn by data 2. So whenever you see the theta can be learned from multiple data sources, we can use SIP, SIP, a selective integrative learning to pull the information. So the theta 1 is actually more enhanced version, not just from one data source. But some representer can only learn from one data source, but doesn't matter, we can still use it, okay? So once we try to learn something for data 1 representation, we can, remember that previously I mentioned that the data 1 can be both theta 1 and theta 1. You see theta 1 and also theta 2 and theta 4, right? So therefore, when you try to represent theta 1, you can retrieve this theta 1 and the theta 4 and the theta 6. And the theta 1 is an enhanced version. And similarly, you can represent the theta 2 using this unique combination of the latent representation, okay? So again, I'm point out this message that we actually can learn the unique information through the unique combination of the latent representation, and some of the representation can be learned from multiple data sources, not just one data source. And this is a blockwise R-squared learning loss function. And this loss function is, you can use whatever loss function you use, except the learner now is a little bit more complicated. It's a concatenated information. Instead of just using one block information, we have multiple sources of information, okay? Okay, so let me also try to see what is the connection to our approach to transfer learning, right? I know some of you work on the transfer learning. So you can think about transfer learning, we have a multiple source data. And through the multiple source data, you actually can learn theta, just like using the R-square. And you can extract a unique representer using SIP and find the F1 and Y1 and FS, YS. This is for the source data. Typically, people are not that interested. But for the target data, they can borrow this, transfer the theta representer to specific target for this source data. Okay, they can learn the representer RT, and therefore we also learn the FT and eventually get the predictor YT for the target data. Okay, so this is we can use this approach to apply for transfer learning. Now I'm going to talk about the numerical study. Right, all the talk seems very interesting, very useful, but we need to show that that really work in the reality. Okay, if it doesn't work, it really doesn't matter, okay? So let's first look at one simulation. We actually have a lot more simulation, but I'm just going to illustrate one simulation. This is for heterogeneous subgroup. So here we have subgroup Y1, Y2, Y3, they share the same coefficient. And Y4, Y5 share another coefficient. So basically we have 4 subgroups. They have very unique coefficients corresponding these 4 subgroups. And I believe Peter Song, they also studied this kind of problem. This is called the posterior drift. We try to use 4 unique coefficient representer to answer the question, can we do the good data integration? So here what we learn, we actually can learn 4 representers just from the data. We don't need to specify how many representers. From the data, we learn 4 presenters and really see that representation 1, clearly that they pull the data 1, 2, 3 together. They believe they have some homogeneity. And the representer 2, similar, I'm not going to explain, okay. And the representing 1 have this kind of a same coefficient, about 0, 1, minus 2, okay. Let's look at the performance, okay. The first one is our proposed method. And second one is the individual learning. Individual learning is I just learn from my own data. I don't want to do any data integration. And the other 2 is by Peter. Sorry, if your approach doesn't look that strong, probably it's my problem, not your problem, okay. And other approach by Duan and the Wang, 23 paper. You notice that in often situations, the data integration actually didn't even perform better than individual learning. Why? Because when the data very noisy, you do data integration. If you don't do the right way, it doesn't help. It just adds more noise. You can see that for data 1, 2, 3, the estimation error is actually bigger for this integration, the other 2, okay? But for us, we can still do pretty well. This is the one, and other I'm going to illustrate 4 real data example, okay? Real data example. The first one, so I was very surprising. She told me we can do data integration for these 3 very heterogeneous image data, MNIST data, K-MNIST, and fashion MNIST. Okay, so let's look at the result. So so actually individual learning already is very, very strong. In general, I will not encourage people to do much comparison for this kind of data, because I would say, look, minister data, the deep learning already did it so well. It's very difficult to improve, right? So even using individual data set, using this K-minus data or Korean-minus data set, this accuracy already achieved about 98%, more than 98%. But using the data integration, we can achieve 99%, more than 99%. So don't underestimate even 1% improvement in this kind of image data competition. It's how hard to even improve 0.5% improvement, okay? So, and actually across all these data sets, we can make the improvement from original 98% or 96% improve to 99 to 97, okay? So this is still very striking. And the second data, we show this pan-cancer data. We studied the 5 different cancer data. So this one also have both covariate shift and posterior drift. They really measure different things, different response. And our approach showing that we can improve the individual learning. This is the smaller is better, okay? The mean square error is the smaller is better. So sometimes bigger is better, this is smaller is better. And across all these 5 different cancers, we are doing better than individual learner and also other competing methods, okay? And also let's look at the adenine data, the block missing data. This is actually very challenging data. If you don't believe it, give it a try, okay? So the response is a mini mental state examination, measure their cognitive function. So here we also have a covariate drift and the posterior drift, and also have a multimodality block missing. So 69% observations are missing, large percentage are missing. And this is our result, the root mean square error. So the smaller is better. We are able to achieve below 4. And if you use the individual data, the root mean square error is much bigger. And our previous paper, I'm very glad, is still doing actually pretty well, about 4.3, okay? And discount the other approach using multiple imputation method. This is actually the poorest, okay? I believe maybe it's also one of my friends' paper. I feel bad now. Again, I'm showing that it's very promising using this BR square, okay? So here's the last slide about the summary. So today, we propose this unified framework for heterogeneous data. The key idea is to try to use the representation retrieval that we hopefully can disentangle many small pieces of representation from different data sources. And therefore, we can pull all this information in a unique way that we can retrieve them in a heterogeneous way, okay? And we use this SIP penalty function to encourage the integrative learning. And also, we talk about the blockwise representation retrieval. How can you retrieve this representer from the multi-source, multi-modality data? And the last message is thank you, and this is the image about the integrative learning. I don't intend to send a political message, but I think it's actually very needed at this time of year, especially for US. And also the last slide is the acknowledgement for all my students, not all my students, is kind of more like recent students who contribute on this data integration topic. Particular for Qixi, you already mentioned his name multiple times. Without his help, I don't think I can deliver this lecture. We went through multiple revision for these slides. I have a team of students who work on the mobile health and neuroscience, optimal transport, and many data integration. And the other color is my collaborators from the Children's Hospital, Eli Lilly, and also UCI School of Nursing faculty who provide the oral ring data, and also neuroscience team study the rodents data, and also my colleague Baba Shubaba, and also two of my long-term collaborators from University of Southern Florida. They actually support funding for my research. So this comes to the conclusion that I like to acknowledge three funding agencies, NSF, continue support my research. I'm very grateful. And National Institute of Health is supporting our research for our mobile health now. And the Simons Foundation, James Simons, very generous, and also support our research through the Mathematician Genius Simons Center. So thank you for your attention, and I'm open for the questions.
Yeah, thank you, Annie, for the very interesting talk. And now we open the floor for questions. Any questions from the audience? Yeah, please.
Any wonderful work. Any limitation, to your method, any caution that, in the example, of course, you show your method is all other methods, right? But any cautions, any kind of, what's the area that this your method will shine? What areas,
Maybe you can repeat the question.
Okay, yeah. So thank you. I believe it's also my former collaborator, that Jack Lee. Okay. So Jack's question that whether there's some limitation for our method. This is a great question. What is the limitation, right? I think there's still many rooms to improve. First, I mentioned about statistical inference. For this talk, I didn't touch anything about statistical inference. I felt it's very, very challenging. So especially if we want to do causal inference, we want to have a specific treatment. We also need to not just estimate the prediction, the classification, but we also want to evaluate the uncertainty, the quantification. So this part, I don't know. So this could be the limitation. I don't know, this is just like another future direction you can explore. I haven't mentioned about the informative missing, right? I talk about the block missing. So what about the missing mechanism? So if the data is informative missing, so let's say this group of patients, they are very, very ill, and therefore doctors say it's wasting my time, or not wasting my time, wasting further observation, right? You don't need to measure this person's the image, because this is no use. So therefore, I haven't addressed that. I don't know the answer. That could also be limitation when the missing mechanism is informative. I believe they also have, let's say, unobserved confounder. So here I'm talking about the data integration wherever I can retrieve, right? I could, a lot of representation, I talk about inner beauty, that cannot be extracted, even though I have this observed information. But this really important, the fundamental things, maybe I'm not able to retrieve. Probably this method will not work. Yeah, so at this time, I can only think about this. Maybe I will think more about more limitation, but thank you for your question.
Any other questions for any?
I try to understand Yifan Liu's question well. So your question is that for the R square, can I retrieve multiple?
So I guess maybe using the label example, you are using how to sort the data. Is it possible that the objective you are targeting, there may be multiple ways to conduct?
Oh, yeah, this is a very good question. Yeah. So I'm going to repeat the question. So here I'm going to do the retriever, right? So let's say for this object. So Yufan's question is there may be multiple different ways to retrieve them. So one thing I want to address, our retriever is really data-driven. We don't impose anything. We just say whatever this representer is useful for my learner, we're going to retrieve. So therefore, it's not like we have a multiple learner. We try to do like a boosting type of this kind of approach. We kind of just doing this all simultaneously. Which representer is useful? And this is, you realize some representers can be learned better because you have a multiple data source. You can learn better, but doesn't matter that if this feature is useful, I'm going to retrieve it. So I don't know if I address your question. So I don't need to worry about the multiple different learner and try to better combine them. Already, when I do this, you can think about the whole representer is already small enough. It's a very small pieces of the representers, disentangled them already in the dictionary. And when I retrieve them, I pull whatever information I want. Okay.
Any other questions? Yeah, Tim, please.
Okay, excellent question. So we come back, yeah, at beginning, I also don't believe it, right? It's 3-minister data, right? I said it's really bizarre because for the computer scientists, they're not going to integrate data from these 3 different images. So what common information we can learn? So this, again, what we want to talk about, a lot of data is like by visualization, by your eyes. They don't look alike, right? Because you don't see what is the true representation, the latent representation. The true latent representation, they could still share because there are a lot of strokes. You wonder, how can the Korean minister has any similarity of the Arabic minister, right? But still, once you have enough data set, the stroke, the edges, the little object, they can still find some similarity through the latent representation, not by your visualization, but it's more like through the inner representation of the data. So in this, actually, we are able to learn. So you notice that we can learn more from minister and the Korean minister compared to the fashion minister. So because the sheer structure between the Korean minister and the minister data compared to the fashion minister is the common structure is less. So therefore, the sharing information is less. But still, nevertheless, you can still make some improvement, okay? Yeah, this is very surprising, but it's all reproducible, okay? So the data, the coding will be shared to everyone later. We actually haven't finished writing the paper yet. So once we finish writing the paper, all this information will be shared to everyone.
So just to follow up with the previous question, what is the practical implication for the results?
The practical information that we can do data integration more than we can imagine. So in a lot of situations, we limit our horizon. We think we can only integrate data if they do this specific same study. But the implication that if you're doing some cancer study, I'm doing the other kinds of cancer study, even we are measuring something different, but because there's some the intrinsic cancer mechanism, this information can be borrowed from very different, diverse cancer data set. So I think I'm very excited because I believe the industry people also will be excited about this.
So if I push the envelope, I want to say that all the images share the same characteristics that image is composed with pixels.
Possible. This is we haven't tried this, right? We have ImageNet. You know, Fei Li has ImageNet. whether this ImageNet can help the K-minus data or the minus data. Chi, are you here? Maybe you already tried this data set. Maybe you can address this question. Oh, Chi, yeah. So you stand up so everyone. Okay, thank you, Chi. And by the way, any other question? Yeah.
Peter, Peter, you can go first, maybe.
Peter Song, you have a question? Yeah, thank you, Peter. And that's what friends for. We're going to, right? I think a few years later, your method will to beat my method.
There's another question there.
Yeah, I couldn't hear too well. You mentioned about the prior distribution. Can you?
It might be like about prior information.
Oh, yeah. So maybe sometimes we have prior information we can also incorporate. So for this data, we haven't talked about the Bayesian method. So, yeah. Yeah, this is an excellent point. So by learning this different representation, this kind of serve the purpose, maybe you can learn what is the prior distribution for this data. So you can think about the connection, the representer we learn from this specific data source, maybe just like the prior distribution in Bayesian world. They talk about what's a prior, and here we don't have a specified prior distribution, but we can learn this prior distribution from these representers, from this specific data. Thank you for your comment. It's excellent.
Any other questions?
Maybe I had misunderstood something, but on the previous slide you mentioned how it allows for a different dimensional thinking space. And I could have misunderstood, but I thought that we were trying to find the similar features in like a shared thinking space. So could you explain maybe briefly about how that allows for the different dimensionality for the data set?
Okay, so the question that if the original data space, right, it's all in the different dimension, how can we, after data integration, we can solve this problem, right? So you can, easy way, I think you try to answer this question, just think about the multimodality question, the each data source, the dimension are different. And also mobile health, the dimensions are different, right? So the key idea is that we try to learn the representers, which is the latent representers, okay? So in a sense that the latent representer eventually we learn is it's like an autoencoder decoder, right? It's like this idea. You encode to the space which share the same dimension, but later on you have to decode back with a different dimension. Yeah, yeah, okay.
Any more questions? Okay, if not, then we'll conclude the lecture. And yeah, congratulations to Annie again.